I'd like to thank the organizers for the great honor to be here to wish Pierre a happy birthday. Je voudrais commencer par remercier Pierre pour l'aide précieuse qu'a apporté la lecture de ses papiers dans le projet de, comme dirait Hopfer, essayer d'apprendre à parler français. The short English translation, if you want to learn French, read Hodge 2 or V1 or whatever. Also, I'd like to say that I sort of felt that very close to the remarks in the opening remarks about the help that Pierre has given to many mathematicians by numerous letters and things like that. So that will sort of be the subject of the talk, as you will see. So let me start. Okay, let me start by recalling, suppose we have X, a smooth projective variety over the complex numbers. Then we can form moduli spaces, or let's think of them as moduli stacks. The Betti moduli space, so these are spaces of representations of the fundamental group of X. The Betti moduli space is just the space of representations of X of pi 1 into GLN, modulo equivalence of representations. So I think it's probably best to stick with a stack quotient for everything today. Then the Durham moduli space is the space of is the moduli space for vector bundles E with an integrable connection nabla. So a connection nabla is an operator satisfying Leibniz rule, and the curvature is 0. And the Dolbeau moduli space is the space of Higgs bundles, which is Higgs bundle is a vector bundle E with a tensor theta. So to sort of, I should say, as we'll see on the next slide, the good thing to notice is that theta really looks like the same thing as nabla, except that it's a linear map, an O-linear map, and the square is 0 again. And in this case, you have to require semi-stability and vanishing of Chern classes and divide by equivalence. So it's good to think of these as some kind of non-abelian first cohomology of X with coefficients in the group GLM. And why did I say that? Okay. What I meant to say here was that we have these isomorphisms, analytic isomorphism between the Betti and the Durham cohomology. So that's like what we saw this morning, but just in the non-abelian version. The non-abelian version is the Riemann-Hilbert correspondence. And then, so I guess this, for this part, you have to say something like either go to the moduli spaces rather than the stacks, or just look at smooth irreducible points or something like that. The topological Durham and topological Dolbeau moduli spaces are the same. Then what I meant to say is on smooth irreducible points, that starts here. Just the topological space. In fact, it's the real analytic manifold. It's not the complex. This is not a complex isomorphism. And in fact, so what Hitchin says is that these two complex structures from here and from here complete to a quaternionic triple. And from a quaternionic triple, the classical Penrose construction gives you a twistor space. So the twistor space is a space mapping to P1 with the property at least that the fibers over, for example, 0 is going to be M Dolbeau, 1 is M Durham, and infinity is M Dolbeau bar. I think we can sort of assume that this was said in Hitchin's paper. And so Deligne, in a letter on March 20th, 1989, I just found the letters relatively recently, because when we moved from Toulouse to Nice, they got stuck in a box which then didn't get opened until just a few months ago. So I was wondering where did these go, but so I was very happy when I finally found them. So Deligne came up with a great interpretation, and as Mr. Goddard said this morning, this taxes this is an example of taxing the resolution of our photocopier. I took the liberty of photocopying onto the transparency. This is page 10 of the letter, and this is the first part of page 11. Let's see, there's maybe a little problem here. I should probably do this. Is that better? A little resolution problem here. Okay, so then maybe let me change the slide here to the next slide. I thought maybe I'd leave that up for a while and go single projector on this side. Okay. But so let's look at what Deligne said in his here. So after the first pages, I think I still probably don't understand the first pages. The letter starts off saying that Witten explained to me, Deligne says, Witten was explaining to me Hitchin's point of view on the twistor space. And so then Deligne explained Witten's explanation of Hitchin's point of view on the twistor space. And then we come down to the question. Assume the answer to the previous question is yes. I forget what that was, the previous question. Then can Z, so can Z is the twistor space here. And S is P1 actually. Can Z over S with this trivialization be described as follows? Okay. So identify S with P1. So S, in fact, S is the sphere, the two-sphere of complex structures on a quaternionic vector space. Then you have some particular ones which are J, I, and minus J. So in Hitchin's notation, J corresponds to 0, I to 1, and minus J to infinity. And for X, our space in V, a vector bundle, the space of connections is the space of connections on a bundle is basically given by H0 of omega 1 and V. I think we're on a curve here. So there's no square condition. So what Deligne said was, let's define the space of lambda connections on a bundle by pushing this principal homogeneous space by the function lambda from H0 omega 1 to H0 omega 1. So this looks like a totally trivial operation, which is that lambda is either 0 or it's a non-positive, or it's a non-zero complex number. So if we push, we either get 0. The map is either 0 or a scalar isomorphism. Okay? So that doesn't look like a very good idea to push by a map which is either 0 or the identity, basically. But in fact, it is. So for lambda different from 0, it's invertible, and the lambda connection is the same thing as a connection. And for lambda equals 0, a lambda connection is a 1 form. But so it turns out when you do what he was saying here, that the connection will be lambda times an actual connection plus a correction term. What that comes down to, in fact, is that, did I write that here? Yeah, I wrote that down here. What that comes down to is that we're going to be looking at operators which look like a connection. In the higher dimensional case, you'd like to include the square of the operator equals 0, the curvature 0. And the Leibniz rule comes down to the usual Leibniz rule, but just with a lambda, sort of just a one little extra thing here, in front of the differential term. And remember, lambda is either equal to 0 or to 1. So this just exactly gives you the difference between the notion of a Higgs bundle and the notion of a connection. Let's see, so let's finish here. Right, then, so Deligne said, let's look at this as a lambda as a parameter and define a moduli space, a parametrized moduli space over the affine line. So then this is again Z. So that Z lambda is the moduli space of bundles with lambda connection. And then what's said here, which is maybe a little bit difficult to read, maybe I should change the focus for the bottom of the screen. So, yeah. So if lambda is different from 0 or infinity, then you can, given the lambda connection, you can multiply by 1 over lambda and you get a usual connection. So and a usual connection is just the same thing as a flat bundle. So you get the space of flat bundles. So what Deligne said, let's identify flat bundles on X with flat bundles on the complex conjugate variety. The complex conjugate variety is determined by taking the equations of the variety, writing them down, and every time you see a complex number, just take its complex conjugate. Okay, that gives you a new algebraic variety defined by new equations. Okay? And the topological spaces are isomorphic by the map which does complex conjugation on coordinates. So for the number theorists in the audience, if you can figure out Frobenius, you can easily figure that out. For the rest of us, it's kind of complicated. Okay, but so anyway, so the spaces are topologically the same, which means that flat bundles on this, which means they have the same fundamental group. So flat bundles on one space are the same thing as flat bundles on the other space. And let's see. So here, Deligne says on P1 minus 0, which means the other chart for P1, let's describe Z as being the space whose fiber over lambda is moduli space of bundles with lambda inverse connection on the complex conjugate variety. Okay. So I found this page of mathematics to be a great revelation. It had a number of consequences. The first thing is that it was an algebraic construction relating M de Rham and M d'Olbeau. So if you recall, Hitchin's isomorphism is given by solving some kind of Yang-Mills-Higgs equations. So fundamentally, we're doing a lot of sort of partial differential equations and things like that. So this doesn't itself give the isomorphism, but it does give some way of thinking of points of M de Rham as being close to points in M d'Olbeau in some sense, but an actual algebraic construction. Then some computations showed, and I'll try to say what those are, showed that this moduli space of lambda connections has to actually be considered as being or as embodying the Hodge filtration on the non-abelian cohomology. Maybe I should recall here that this is H1 de Rham of X with coefficients in GLN. So if we think of these moduli spaces as being non-abelian cohomology, then it's reasonable to think that they should have a Hodge filtration. Okay? And as I'll try to more or less show here, it becomes apparent that this space of lambda connections is actually the Hodge filtration. Okay, so in view of that interpretation, let's call it M Hodge, which is, so it's a moduli space which maps to the affine line, and it's the space of vector bundles with connection satisfying the lambda version of Leibniz rule. Okay, so now let me try to explain why we should say that that is the Hodge filtration. So the first observation, and I think this observation pretty much is due to Deligne. He didn't actually say as much in the letter, but he had some comment saying that if you had a weight 1 Hodge structure, then you could form the twistor space in a similar way. And in that case, the Hodge filtration of the Hodge structure gave you this lambda part of the filtration. So anyway, you can see that there's a nice equivalence of categories between filtered vector spaces and bundles, vector bundles on the algebraic stack you obtain by dividing the affine line by the GM action. In this correspondence, so maybe I should say this stack has 2 points. It has a point 0, which is actually an algebraic stack. 0 is a BGM. And it has 1, which is an open substack. 1 is a point, but which is an open substack. So this is a stack which has 2 points, which are sort of glued together, an open point and a closed point. The open point is an open subset, and the closed point is a stack. It's not just a point. And as we saw before, the space of lambda connections for different lambdas, which are different but not equal to 0, are all isomorphic. So it's good to think of to take the quotient by this GM action and think of it as a space which just has 2 different points. Okay? But so in general, of course, the vector bundle on this quotient stack is the same thing as a GM equivariant vector bundle on A1. And the correspondence goes by looking at order of growth of sections. If you take a section of the bundle that's equivariant by GM, it's going to have a certain order of 0 or pole when you go to the origin, and that tells you what level of the filtration it stays in. Okay, so the fibers at lambda different from 0 are M Durham, and at lambda equal to 0 are M Dolbeau. And I mean, I think I had sort of noticed that this should be called Dolbeau cohomology, and that's not really a mathematical remark, but a linguistic remark. The space of Higgs bundles is naturally, you should naturally think of it as a Dolbeau cohomology, because a bundle is like a coherent, like an element of H1OX, and a Higgs field is like a form, like a one form. So it's sort of elements of H1OX plus elements of H0 omega 1x, but then with a non-abelian thing going on in between them. And so if you got something, if you know that for vector spaces, filtrations are the same as objects over this quotient stack, and if you know that in general, in this vector space correspondence, the object, the fiber over 1 is the original vector space, and the fiber over 0 is the associated graded of the vector, of the filtration. The GM action gives you the grading of the associated graded. Once you know that, and if you remark that in this space of lambda connections, the fiber over 1 is M Durham and the fiber over 0 is the Dolbeau cohomology, then I mean it's sort of obvious that you're talking about the Hodge filtration, right? You're talking about something which is a non-abelian thing that looks like a filtration, and where the associated graded is the Dolbeau cohomology. Okay. Then, of course, the final thing to notice is that if you have a point E, if you have an E, so I'm not saying what E is here, but let's take a harmonic bundle E. Sorry. Okay, so if you take a E which is a harmonic bundle, or say a variation of Hodge structure or something like that, then as Deligne pointed out elsewhere in the letter, that gives you a preferred section of the twistor space. And if you calculate the normal bundle to this Hodge construction along this preferred section, then you get exactly this C construction that we had in number 1 for the tangent space of the space of representations with its usual Hodge filtration. So that means that on the level of tangent spaces, this M Hodge on the level of tangent spaces really corresponds to the Hodge filtration. Let's see. Here. Let's see here. Okay, now Deligne's gluing. Did I? Right. I didn't write down what that was, but so the gluing, which I just erased here, maybe I should. Can I take this one off? Okay. The gluing that was referred to down here can be considered as, so let's glue M Hodge with M Hodge bar, with M Hodge of X bar, and glue it along M Durham, which is the Betty moduli space, which is, yeah, here. I guess I did it here, okay. Okay, so I didn't need to take that off, but, okay, so I explained here the gluing, okay. So, but let me say that this gives a complex analytic construction, the gluing, which I'll explain here, gives a complex analytic construction of the twistor space. And Hitchin had constructed the twistor space by taking the moduli space of bundles, which was, for him, in fact, sort of equally the same as the space of representations or the space of Higgs fields, noticing that it had two complex structures and constructing the twistor space by defining it by Penrose's construction for a quaternionic manifold. So fundamentally, that somehow or other that uses Yang-Mills equations, because to get the correspondence between, to get the different complex structures, you need to solve Yang-Mills equations to relate Higgs bundles and representations. And so Deligne's construction gave a complex analytic construction. It's not an algebraic construction, but it's a complex analytic construction of this twistor space. And we can hope, maybe that wasn't what I wanted to talk about. We could hope, in fact, that that you might actually be able to reconstruct this Yang-Mills correspondence by isolating in some way the set of preferred sections, And Deligne proposed what looks sort of like a way of isolating the preferred sections, namely they're sections which are preserved by an involution. And Hitchin in his paper says that all the sections preserved by an involution on the Toaster space are preferred sections, but doesn't prove it, and I actually see no way whatsoever to prove that. So I think that has to be assumed as a conjecture, that maybe in this case, I mean, it's true that these sections are a connected component. I mean, a tangent calculation says that the preferred sections form a connected component of the space of all sections which are preserved by the involution, but I don't see any reason why there shouldn't be some other strange ones. Okay, let's see. So now what do we have? We have this M Hodge. So I'm going to sort of oscillate between taking the quotient by GM or not taking the quotient by GM. If we take the quotient by GM, then it maps to the quotient stack. And there's only 2 points in the quotient stack. So you have M Duram over the point 1, which is an open substack, and M Dolbeau over the point 0. Now let's explain the gluing. The gluing is easier to understand if we take that quotient, because in that case, M Duram is an open substack of M Hodge. It's also M Duram of X bar is an open substack of M Hodge of X bar. So we can just glue the two together. I should have put analytic here. We can glue the two together by exactly what Deligne said, which is that M Duram of X GLN is the space of representations, embedding, and representations of pi 1 of X are the same as representations of pi 1 of X bar, because X is isomorphic to X bar by complex conjugation, and so that's isomorphic to M Duram of X bar analytic. So we have this, I should have put analytic here. We have this isomorphism here, and you can just take the colimit of this diagram. You're just gluing together two complex analytic spaces over, except they're stacks, but over a common open subset. Okay, so we get a guy which of course maps to P, which is the quotient of P1 by GM, which again is glued by two copies of A in the same way. And then what Deligne was saying was that this would give Hitchin's twistor space. So I was able to prove that by, or maybe I should say try to prove that, by doing some sort of a slightly roundabout way, noticing that is a twistor space for a quaternionic structure, then calculating that it happens to be the same quaternionic structure as Hitchin's one. So let's see. Now, an interesting thing which goes back to the normal bundle calculation is that if you take a preferred section, I'm not saying what preferred sections are here, but I didn't want to talk about that too much. If you have a harmonic bundle, then the harmonic bundle equations, which are these Yang-Mills equations, allow you to write down a family of lambda connections for any different lambda, even lambda equals infinity. So you get a section of this twistor space, a section being I mean, here we got a space over the quotient P1, and then the twistor space is the fiber product of this space over the quotient by P1. Okay, so it maps to P1. And by a section, I mean a map from P1 back into here. Okay. And a preferred section is a section which comes out of the harmonic bundle equations, which comes from a harmonic bundle in a way which I'm not writing down here. So an interesting thing is that the formal neighborhood of a preferred section, so take a preferred section and look at each fiber, take the formal completion, then use the ideal to filter that guy. That's actually a mixed twistor structure. And so to simplify, if the preferred section happened to come from a variation of Hodge structure, that's a mixed Hodge structure. The notion of mixed twistor structure was in fact actually suggested by this construction. So given this whole business about lambda connections, filtrations, and so on, a notion of a mixed twistor structure is like a mixed Hodge structure, except you forget the Hodge filtration, and you just look at the family over P1. So it's a twistor is something over P1 where it's not necessarily GM equivariant, and then the weight is being a pure of a given weight is that it's a semi-stable bundle over P1. And a mixed twistor structure is a guy with a weight filtration, such that it's a bundle over P1 with a weight filtration, such that the quotients are semi-stable of their respective weights. And that actually gives you a theory which works identically to a mixed Hodge theory. And that's there to deal with preferred sections which are not themselves variations of Hodge structure. So they're not preserved by the GM action. You see, GM, the analytic GM acts on the whole thing, which basically because we took this fiber product here. So you have some sections are actually the variations of Hodge structure are sections from this round P back up to the Deligne gluing. And twistor sections are just sections defined on the P1. Then the final nail in the construction, which sort of really shows how this was at least from my point of view, was an incredibly fruitful observation, which came from that letter, is that if you take the space M Hodge, the Hodge filtration, take out the nilpotent Higgs bundles. So by Higgs bundle, that means something lying over lambda equals 0. And nilpotent means you want the Higgs field to be nilpotent. So throw all those guys out. Then take the quotient by the GM action. That's actually a compactification of M Durham. And in a sort of philosophical sense, maybe, what that seems to mean is that the Hodge filtration somehow is concentrated at infinity in the space of connections, in the space of representations. Whereas from the previous line, the weight filtration, on the other hand, seems to in some philosophical sense, be concentrated at around finite points. You're always taking this completion with respect to some kind of augmentation ideal or something like that, which in this case means just completing with respect to the ideal of a point. So the weight filtration sort of is in the finite region, and the Hodge filtration, in some vague sense, is at infinity of the space of connections. And so when I say relationship, I don't mean any particular relationship, but I mean this compactification sort of represents what you might call singular perturbations. So in fact, I think in that sense, you should say that this whole notion of lambda connection actually goes back to Liouville and Liouville was talking about lambda connections. Liouville had differential equations with an epsilon parameter in front of the differentiation. Okay, so on an a priori level, this suggestion of looking at lambda connections was opened up a number of new things. And so it's actually, seems to me at least, pretty natural to look for directions of generalization of the theory. Now, one obvious direction of generalization of the theory is to look at open varieties, but that's actually very hard. And I mean, I wouldn't say there's been, now I say there's been important progress. I'm not sure to what extent these people have actually done maybe Pierre doesn't seem to be able to see the bottom of the screen. So Takuro Mochizuki and Claude Sabat have extensively worked out the theory of harmonic bundles on open varieties. One ingredient, in fact, was this notion of mixed twistor structure. Because you need to, that replaces the mixed Hodge structures which are used by Katani, Kaplan, and Schmidt, and Kashiwa, Kawai, and so on. And then I'm not sure to what extent they sort of looked at this space of lambda connections, but it seems obvious that you could try to do that. That could be interesting. But it's very hard work, and so we're not going to do that today. What we're going to do today is, might look also frightening, but it's actually very formal. So now another direction is so instead of generalizing on the variety X, another direction is to try to generalize this H1, this non-abelian H1, try to replace it by some kind of higher non-abelian cohomology. So the first task is to try to figure out what higher non-abelian cohomology actually means. So one way of looking at that is that here we've been looking at H1x with coefficients in GLN. One way of thinking about that is to think of it as a space of maps from some kind of X thing, which we'll see in a minute, to BGLN. That's the island, that's the American school, maybe I should say. Cohomology is, Eilenberg-MacLane spaces and so on. Cohomology is given by maps from your space into some space. So let's just look at try to do the same thing. So try to invent some kind of T to put there and look at maps from X, from some super X thing into T. Okay. Let's see here. So now, what I'm going to talk about today is an example which arises very naturally, which is sort of, it seems to me like a good, aside being the thing which I was just working on recently, it also seems to be a good sort of introduction into this non-abelian cohomology, because it gives you a natural example of something to put here, a T, which doesn't seem to be totally trivial, but which you can sort of motivate starting from, we're not just going to introduce it, out of nowhere. We're not just going to pull it out of the hat. I'd like to motivate why you would want to look at this thing by stuff which I hope people will be familiar with here. So let's consider the following example. Let's suppose we have a smooth morphism f from x to y between smooth projective varieties, say. And suppose we have a vector bundle with connection in the Durham moduli space of x. Then let's look at the higher direct image, the higher Durham direct image. Of course, that means tensor E with the relative Durham complex and so on. And then we apply its Gauss-Manin connection. You get an element of M Durham of y, coefficients in GL of Mi. But Mi is an integer which depends on I. And it also depends on E, nabla. And everybody's obviously familiar with this phenomenon. The dimension of cohomology can jump when you move things around, right? So when you move around E nabla, when E nabla moves around inside the moduli space of representations or bundles with connection, then of course the dimensions can jump, and this is a sort of standard hurdle for all sorts of things. So let me just give a totally concrete example. So suppose we take an abelian variety, a three-dimensional abelian variety, look at a hypersurface. Let's take here y as a point. This basically happens when y is a point. Then let's look at the Hodge numbers just to sort of get everybody understanding what's going on here. Let's look at the Hodge numbers of x with coefficients in the trivial local system. So of course it comes from the abelian variety, 1, 3, 3, and then 3, 9, 3. And since y is a two-dimensional variety, you have new cohomology in the middle dimension. So 3 plus a, 9 plus b, and 3 plus a. And then the dimensions above the middle dimension go back to the same as the lower dimensions by Lefschetz. Okay. On the other hand, so let's suppose, for example, that A is a simple abelian variety. Suppose we have a different line bundle with integrable connection, and let me just take this opportunity to point out that the moduli space M Durham of x with coefficients in GL1 is what's known to number theorists as the universal extension of the dual abelian variety. Suppose we have a guy which is different from the identity local system. Then by the generic vanishing theorem of Green and Lazarfeld, all the stuff except in the middle dimension vanishes. And by calculating the Euler characteristic stays the same in all this jumping stuff. So the dimension of the cohomology is 5 plus 2a plus b in degree 2 and 0 in degree different from 2. So all this stuff here and here sort of collapsed out, and we just get to the stuff which has a different dimension in the middle dimension. Okay. And so here's something which I think is true, but I didn't actually write down the proof of that recently. So you get a vector bundle, you clearly get a vector bundle of rank 5 plus 2a plus b on the complement of the origin in the moduli space. The thing which I think is true is that the vector bundle does not, in general, actually extend across the origin. So the map that you get from the complement of the origin in the Durham moduli space to BGL of 5 plus 2a plus b, that means a vector bundle, does not extend across the origin, I don't think. I didn't actually calculate the example explicitly, but I think that a while ago I thought I calculated something which said that that had a singularity which wasn't going to extend. So in any case, I don't think it extends, but in fact, even if it did extend it, we would still want to do something other than that. Okay, so of course the solution of this problem, pretty obviously, is that we'd like to look at the full R F lower star Durham, which is the full complex higher direct image. So it's an element of the derived category of dy modules, which is O perfect, because we assumed it was a smooth morphism. So there's no, I mean, D module people love singular stuff and stuff like that, but actually D modules are also very interesting even when there's no singularities. And since I don't understand what's going on in the singularities, then let's just take the non-singular things to start off with. But here the best thing to do, and I think this is something which I would love to sort of discuss the history of this whole thing, because this is, I'm not completely sure why so many people did so much stuff with the derived category, but not taking the differential graded category as the derived category. And in fact, I think this was first done for O modules by Bondal-Kapranov. But I think that, for example, in the Gabriel Ziesman book, in the back of Gabriel Ziesman, there's a big discussion of differential graded categories, which is obviously intended for exactly this purpose. They even take the 2 category associated to a differential graded category by truncating. And since they don't know how to do an n category, they don't. But I mean, obviously, if they did know how to do an n category, they would have done an n category. So I mean, in a certain sense, this is sort of very old, and in another sense, it's sort of very new in the sense that we're just now starting to actually use that, I guess. So, but it's best to look at the differential graded category instead of the derived category. And Bondal-Kapranov called this I think the extended or enhanced triangulated category. And whenever you hear theorems like Orlov's theorem about differential graded category of the product is the space of morphisms and so on, that always means actually now the differential graded category, the enhanced derived category. So now when people say differential graded category, now when people say derived category, they don't really mean the classic old derived category, which is just a 1 category. They actually mean it. I mean, if you press them, you'll find that this is the case. They actually mean the enhanced differential graded category. Okay, so now, of course, this does pose a certain number of problems, how to actually deal with this notion. And one of the main constructions which you'd like to do is to apply the Dold-Poupé construction. So the Dold-Poupé construction, I'll remind everybody, takes chain complexes and sends them to simplicial abelian groups. And it's the inverse of the normalization complex functor, going from simplicial abelian groups to chain complexes. And that was given an equivalence of categories between chain complexes of abelian groups supported in the negative degrees and simplicial abelian groups. So Dold-Poupé is 1/2 of that equivalence. And the thing which I found not easy to find, but Dale says that he'll send me tons of really old references, is that the Dold-Poupé, this construction, is actually compatible with multiplication, which means that it extends to a construction that works on enriched categories. So we can apply it to the enrichment and go from a differential graded category to a simplicial category. A simplicial category means a category enriched in simplicial sets. Or if you don't like those, think of topological spaces. And it should be noticed that this construction truncates in degree less than or equal to 0, and Maxime would, of course, say, no, this is not what you're supposed to do because you want to keep the full derived stuff in positive degrees. So whenever you hear derived algebraic geometry or derived something or other, that always means you're actually trying to keep the stuff in positive degrees. But I mean, this construction just applied as is truncates, so let's just truncate. And so simplicial categories are a good way of thinking of one-groupic infinity categories. Let me put that slide up. Where was that? I'll get to that in a minute. Okay. Then we can take the Dold-Poupé, enriched Dold-Poupé construction applied to this differential graded category. And that gives you a simplicial category, which can also has lots of other ways to calculate it, namely simplicial model categories or simplicial localization of Dwyer-Kahn. And then let's let that vary with parameters, and we get an infinity stack. So let's call that M Durham of X perf. Okay. So guess what sort of slipped by here is up here, these are O perfect. So what O perfect means is that the complex of O modules on Y, this is well known, it comes in Mumford's abelian, most of Mumford's little books have an initial section which proves this theorem. If you take something like the direct image of the de Rham complex, you can replace it by a complex which is quasi-isomorphic to you can replace it up to quasi-isomorphism by a complex of vector bundles on the base. Of course, that's not going to preserve the D module structure, which is the subject of the rest of the talk. So that's what O perfect means. Okay. And so then well, this is sort of notation. I probably should put the next slide up, actually. This slide had so much notation which relates to future slides that was kind of bogging us down here. Now I should be going faster. Okay, so now let me speed up a little bit here to try to get through my slides for the end of the talk. Okay, so sorry for those who wanted to go slower, but so we get an infinity stack called M de Rham X perf, which is obtained by applying this Dold-Puppe construction to the derived category of D modules, and letting this vary as in parameters. So Z is a parameter stack, parameter scheme. Sorry. And convention by O perfect, we mean O perfect of bounded amplitude. That means that it's a bounded complex of vector bundles. Okay. And that actually has the property that means that these simplicial categories have simplicial mapping spaces which are n truncated, and n is the amplitude. So in fact, they're n plus 1 categories. So it's locally an n stack, but n varies globally. And so I didn't put any sort of superscript here. So that means that we're looking at perfect complexes which could have arbitrary amplitude but bounded amplitude. So it's really an n stack, but it's just sort of locally an n stack, and n varies. Then let's go back to our motivating example of why we got to this guy. Why we got to this, remember why we got here, was because we wanted to look at the higher direct image. So we started with a higher direct image defined on the de Rham moduli space of GLN. But of course, that's a subspace of the full space of perfect complexes. And you can just define the higher direct image, the de Rham higher direct image, from the moduli space of perfect complexes of X, and it goes to the moduli space of perfect complexes of Y. So that's sort of, you might think, motivation for why we want to introduce this. Because of the jumping of dimensions, you cannot give this map just on the usual one stack moduli spaces. This map only exists when we go to this n stack type of thing. Okay. Of course, it exists most places, on a stratification and so on, but if you want to sort of get a nice map which exists everywhere and sort of formally does all the things you'd want it to do and so on, you have to go to these guys. Okay. So let me backtrack and say this was a suggestion of Andrei Hirschowitz to look at the infinity stack of perfect complexes, perf. And whereas here I said define M de Rham of X perf to be obtained by some category of D modules and then take Dold-Puppe of it, you could also say let's just look directly at the stack perf, which is the stack of perfect complexes over a point. That's non-trivial, of course, because we always have to introduce a parameter scheme. Okay. And then define M de Rham X perf as Hom from X de Rham into this stack perf. This is the Hom of n stacks, or infinity stacks. And X de Rham, of course, is the thing which is associated to the de Rham formal category, which I discovered in Berthelot's book about crystalline cohomology. So you have in characteristic 0, you have a really easy example of a formal category, which is just take X, and that's the object, and the morphism object is the formal completion of the diagonal, and that's a category, a groupoid, in fact. That sort of, and crystalline cohomology is sort of doing that in characteristic P, which is not easy at all, and I wouldn't like to say anything about. But anyway, in characteristic 0, that gives actually, in fact, it's not actually a stack. You'd think it would be a stack, but it's not. It's just a sheaf. And it's the sheaf which to a scheme V associates maps from V reduced into X. And so now we get two different ways of defining the Hodge filtration so we'd think of that as some kind of non-abelian de Rham cohomology of X with coefficients in this stack of perfect complexes. And two different ways of defining the Hodge filtration. One is to take this Hom construction, do Hom of X Hodge. So X Hodge is you take this formal stack X duram, this formal category X duram, and sort of deform the mapping space to its own normal cone. And that gives you a new formal category, which is sort of trivial. It's just the completion of the tangent bundle along the 0 section. And so you have and the deformation to the normal cone is a family over A1 whose fiber over 0 is the X Dolbeau formal category, which is the completion of it's sort of an abelian formal category. Not abelian category, but it's sort of a commutative formal category where there's only objects which have endomorphisms, and the endomorphisms of an object is the formal completion of the tangent space. So that's the Dolbeau guy, and then of course at any lambda different from 0, it's the X duram. That's one way, and then we can now it's a stack. You can define a stack and then look at the sort of relative mapping space from here over relative to A1 into perf, and you have to put a prime up there because at lambda equals 0, you need to require semi-stability and vanishing Chern classes. Then the other way of doing it is to take lambda, which is the Riesz ring of the ring dx of differential operators. So remember, dx is the union of differential operators of order R over R. And this is actually the Hodge filtration on dx. And if you take the Riesz construction, the Riesz construction is sort of it's what was called Xi a while ago. But in this case, it's easy to write down. I mean, you can just write it down explicitly. It's just the direct sum of these rth pieces. That's actually an algebra. That's the Riesz algebra. We'll see that coming back in a minute. And then a sort of thing which is not easy to prove, and I don't think I actually have really proved it, or even tried to prove it, but I mean, did state it, is that these two give the same thing. And then also formally, this RF lower star preserves the Hodge filtration in the sense that it extends to a map on these M Hodge guys. That's also pretty formal. So let's see. Yeah. Now as I said before, you can think of this as just all coming out from the project of generalizing the whole lambda connection business. So, now once we got in here, we can go back and say, we can just sort of formally generalize everything we did before into this case. So for example, we can do Deligne's gluing. The M duram X perf is an open substack of M Hodge X perf. So we can do the gluing and get an M Deligne X perf mapping to either this round P or P1. Maybe you should put depending on whether you take the quotient by GM or not. Then another thing, this is pretty sort of conjectural, you might say, but it should obviously be true, which is that Saito's mixed Hodge modules, or the analogous mixed twister modules, which is the same thing but done using mixed twister structure, which I think Saba did, give preferred sections of this it's not really a twister space, but it's sort of like a twister space. And then you would conjecture that in some sense, the formal neighborhood of a preferred section would be a non-abelian mixed Hodge structure. And so this fits into our project with Ludmil, Katsarkov, and Tony Pantev, where we'd like to investigate what non-abelian mixed Hodge structures mean. So we wrote a preprint which had a couple of theorems and lots of conjectures in it about that. So then you would conjecture that in this case also the same thing holds, that the formal neighborhood of a preferred section would be a mixed Hodge structure. Okay, so up to here we've just sort of done formal stuff. There's not really anything to prove up till now. Then a question is, what kind of nice properties do these guys have? Because here we've just defined them as stacks. So that's like, instead of talking about schemes, just talking about functors, replacing schemes by functors. But there's lots of functors which are not schemes, right? So, there's even lots of stacks in the sense of Grothendieck, just, stacks, meaning sheaves of categories satisfying descent, but which are not Artin algebraic stacks. So let me I think I'll just put this slide up and then go over here and anybody who wants to read it is welcome to, but we don't really have time to discuss it. Then I'll put this slide up too. I actually, last night, I sort of inserted these two slides. I thought I should give some details about what's going on, but I don't think we really have time to read them very well. But so there, there's a whole theory of n stacks, which you can get on that screen. And actually, it's kind of irrelevant to know what an n category is here, because here, I'll follow Faltings and make a current events joke, but maybe I should put a little American flag here, because that's the American school. Sorry? No, but I said that, yeah, you made some current events jokes, which so that was intended as a current events joke. I don't know if anybody's noticed it. When you come back from France, you notice that all of a sudden there's American flags all over the place. Which, I'm not against, but it seems sort of different, you might say. Okay, so but once you have so as I was saying, the notion of simplicial category is actually perfectly good for talking about stacks. But what's actually nice is to know that there exists a theory of n stacks. And once you know that it exists, then you notice that you don't actually really need it. But if you didn't know that it existed, then you would be sort of worried about whether you were doing the right thing or not. But once you know that it exists, I mean, it might not be the right thing, but I think it's the right thing. Once you know that it exists, then you can sort of forget about it. But what you can do here is you can do an analog of Artin's definition of algebraic stacks. And Charles Walter pointed out when we were discussing this in Nice a long time ago that that's sort of what led to this definition, in fact. But Charles pointed out that just for the case of one stacks, the Artin's terminology of algebraic is not really a good idea, because any functor over this category of schemes is sort of algebraic in some sense. What this should really be called is geometric. So Charles proposed that you call algebraic stacks geometric stacks even for one stacks. So let's call these geometric n stacks. That's where that terminology came from. I think Charles was actually thinking of the case n equals 2 also. So I think this is sort of due to him. So the point is that this looks complicated, but it's actually easy to do. You just recopy Artin's definition of an algebraic stack, but iterate it. So you want an algebraic stack is something where you have a smooth chart from a scheme with the property that when you look at the space, the mapping space, the fiber product of two different schemes, it's again a geometric n minus 1 stack. And that's iterative over n. And if n is finite, that's why I was saying before that locally our guys are n stacks. So locally n is always finite, and you always get down to 0. At 0, you should put algebraic space. So then I'll ignore those guys too. So let me put the theorem up now. So then the theorem, of course, is that this m diram of x perf and m hodge of x perf are locally geometric or locally n stacks. They're locally n, and as I said before, and they're locally geometric n stacks where for each open piece you use n, which is different, but you use n to do this iterative definition. Okay, so the theorem is that these guys are actually geometric n stacks, which somehow there means that should be thought of as meaning that they're sort of nice geometric objects, which you could do algebraic geometry with. So they are n stacks, but that's sort of irrelevant, and you should just think of them as being like algebraic stacks. And they map by geometric maps to perf, which is the infinity stack of the locally n stack again of perfect complexes on X. So let me say a couple of basic introductory things about the proof. One is that it seems to me that Jacob-Lurie's representability theorem should probably allow you to prove this type of thing in sort of in all generality and without really even using the fact that without using the particular nature of the definition. I mean, there should be some kind of criterion like the Artin criteria for algebraic stacks. I think Jacob's doing this in his thesis, which is constantly under revision, as I understand, or I don't know. I mean, well, he's going to send me a copy. Get a copy. Anyway, so I don't know how to do that. So what we're going to do is we're going to use a recent result of Bertrand Tohen and Michel Vaquier they prove that perf of x is locally geometric n stack, and they use sort of Bailenson type reasoning. So it should be noted that what's fundamentally going on here is some kind of Bailenson type reasoning. And you might ask, it might be possible to use that directly on this problem. I'm not sure. But so what we're going to do is we're going to say, let's look at so this perf of x, it's sort of perf of x is kind of the non-abelian cohomology of x rather than x Durham with coefficients in perf. So we're going to use that result for perf of x. So that means that we know how to parameterize perfect complexes on x relative to the base point, relative to the base. And we're just going to look at the map from M Hodge or M Durham. So let's ignore M Hodge from now on. So let's just look at the M Durham case, but of course the point was to do it for M Hodge, but we'll treat M Durham. So the question is, given a perfect complex of vector bundles on X, what are the possible structures of complex of D modules on E? And we're going to send, and so I was discussing sort of, discussing math with Ezra this summer, and he was explaining that, his point of view on Kontsevich's philosophy of looking at, of using weak structures, and so that sort of led to this idea to do this. So let's use Kontsevich's philosophy. Kontsevich's philosophy is that if we want to actually calculate something, that we should actually use weak structures. So in Kontsevich's original case, I mean, I'm not able to say what the original case was. I think it was the case of A infinity categories and taking deformations. So the idea was to calculate the notion of deformation of a category, say a simplicial category, a higher category, or a differential graded category. You should replace it by the weak notion of A infinity category, and then you get a much better calculation. So that's an interesting thing. And so let's just apply that here. And this is kind of like more of an exercise of this type of thing, because it's not all that nonlinear. It's pretty linear. So let's define a notion of weak structure of complex of D modules. Now, here's one trick. This trick seems to be important for the proof, although one would hope that one could do the proof without using it. But the trick is that given a lambda, for example, here lambda is dx, given a sheaf of rings of differential operators on x, we'd like to look at lambda module structures. And suppose it's filtered like dx is. The trick is to replace lambda by the Riesz algebra of lambda. Remember that was the, that's the thing we did before. It's for the dx modules, it's the direct sum of the dxr. Okay? So now it's a graded sheaf of algebras, a sheaf of rings of differential operators, rather than just being a filtered sheaf of rings of differential operators. And you can reduce the moduli problem to the same problem for this upsilon. I'll skip that. Okay, so now what do we do? So let me also put this slide. So as I'm explaining what we'll do, let me put this slide over here. So I wrote down the first few terms of what's happening on this slide. So here's the first few terms of what's happening here. So let's take the tensor algebra of upsilon, but it's the tensor algebra over OX. I didn't write that down here. It's the tensor algebra where you take in the tensor products, you put an OX underneath the tensor product sign. And of course, this upsilon is not a commutative sheaf of rings. It's sort of, there's a grading, there's a filtration, and the associated graded is a polynomial ring. So sort of, after you sort of go down in the filtration, it sort of looks pretty commutative, but it's not really commutative. So it's a left OX module and a right OX module. In the tensor product, you put OX in between and sort of use the left and right structures at each point. So let's take the tensor algebra, and this gives you the Hochschild homology complex, and it has a coproduct. And then let's just define QEF to be Hom. So E and F here are complexes of vector bundles on X. Let's look at the Hom complex of the tensor algebra, tensor E with F. And this QEF forms a differential graded category as you let E and F vary. So for each E and F, this guy is a complex. And a Maurer-Cartan complex is a pair. It's a complex E plus a Maurer-Cartan element of QEE in degree 1, such that d eta plus eta squared equals 0. And so I wrote down here what the first few terms of that mean. And I mean, this is actually totally classical for associative algebras and so on. So It's there. It's the bar complex. And so the idea is that that's what a weak complex is. So that's a weak structure of lambda module. Namely, you can multiply by elements of the ring, but you only have the product rule is only true up to the differential of a higher homotopy. And then Hochschild tells you how to organize all these higher homotopies together. So that's our notion of weak complexes. So the first theorem is that is called the coherence result, which is that actually this is a vacuous notion. Namely, it's the same as complexes of D modules. Okay. So that's sort of the general property of this Kontevich philosophy, which is that whenever you hear a talk where somebody's saying, let's do A infinity this, or B infinity, or G infinity, or L infinity, or whatever, you can always say, oh, that's okay. Those are all just equivalent to the usual standard strict guys that we already knew about. So that's coherence. But of course, the point is that it is true that they're equivalent, but the point is not that it's introducing a new notion. The point is that it's a better way of looking at the notion, and it's a way which allows you to actually calculate what's going on. Okay. And so this has some nice properties, besides coherence, one of which is homotopy. This is the fundamental property, which is that if you have a quasi-isomorphism between two different complexes, and if you have a Mohr-Cartan element on E, then you get a Mohr-Cartan element on F. And that's what's allowing us to calculate the fiber product that you need to calculate in the definition of geometric. That's what's allowing us to look at the fiber of this map. And in technical terms, Julia Bergner recently gave a model category structure on the category of on the simplicial categories, where the fibrant condition is exactly this homotopy condition. Okay. So this says that it's fibrant in the sense of Bergner. Then Bertrand-Tohen, but I put Bergner because Bertrand-Tohen did this after Bergner's preprint. Bertrand-Tohen gave the same definition of fibrant for differential graded categories. Okay, so in terms of differential graded categories, it's fibrant in the sense of Tohen, but the basic point is that when you apply Dold-Puppe, you get fibrant in the sense of Bergner, so you can calculate the homotopy fiber. If you like what's going on here, and this I think this is an interesting thing in its own right. What's going on here is you'd like to look at complexes of D modules which over O are quasi-isomorphic to your given complex E. That notion brings in a new complex of D modules, which is generally very big. It's sort of free D modules and so on. And this homotopy property allows you to translate the D module structure on the big complex to a weak structure on the given complex. So you can just calculate with your given complex. That's the point of what's going on here. Then the other thing which makes the proof work is that the Hochschild cohomology of dx is finite dimensional. So I found this in a paper of Wojcicki, but also apparently Berlinski and Getzler. That means that, and remember that we had this, remember that we took upsilon as a graded ring. So these Q, these guys which are sort of Hochschild cohomology complexes, have an additional grading by the degree of the differential operator. And remember, we took the Riesz algebra exactly so that we could call that a grading rather than a filtration. So this is really graded by degree. And these guys, since it's finite dimensional, they obviously become acyclic for big enough K. And this replaces the use of Artinian local rings in the Deligne, Schlesinger, Stashev, Golden, and Milson deformation theory, where you have a differential graded algebra and you like to create a formal deformation space. You use the fact that you're taking Artinian rings as coefficients. So there's some nilpotence there. And here you don't need the Artinian rings, and that corresponds to the fact that the fiber of the space of connections on a given bundle is an affine space, and you get it by the Mohr-Cartan equation. You get the full fiber, not just the completion. Okay. Then you also have to do Hinich and Toledo-Tong style check localization, then a Bailenson style replacing check by a finite complex where you allow only a finite number of poles. So here's the conclusion, which is that you can actually write down an explicit finite dimensional differential graded algebra. This is finite dimensional for each n here, for each degree. I mean, the n contributes to the degree, so the only thing infinite in my expression is here, but that gives you big stuff. So that gives you positive degree, but not negative degrees. So in each degree, this is a finite dimensional differential graded algebra such that the Mohr-Cartan elements of those guys parameterize lambda module structure, or upsilon module structures on our given complex of vector bundles. This is the smooth chart for geometric n stacks for property 1, and property 2 is basically easy. Okay. I'll stop.
Comments or questions?
So one question is, in terms of M de Rham, is there anything that doesn't work algebraically, that is at least in characteristic 0?
That's where you go back to this business about mixed Hodge complexes and mixed twistor complexes giving preferred sections. Remember in Deligne's original picture, well, of course, the gluing is complex analytic. It comes from the Riemann-Hilbert correspondence, which is complex analytic, and that's the case here. No, in the M de Rham, no, but remember the M de Rham is only half of the twistor space. It's the half over the standard affine line. Then you want to glue to the other half, and the gluing in the middle uses the Riemann-Hilbert correspondence, which is complex analytic. And the notion of preferred sections uses sort of Yang-Mills equations, and that goes on here. You might have noticed a few slides back, something that said where if you had a mixed twistor complex, then you get a preferred section of this guy. So that's where something analytic is going on. But no, that's the whole point of Deligne's letter is that this part of the Hitchens twistor space is totally algebraic.